The plan is we'll try to break on time for lunch. I guess we're about 5 minutes late, so we'll maybe stretch that a little bit. But the first talk of the second session is... Yeah.
Speak up.
Okay, we're going to be starting now.
Listen.
Yes. I need a little bell or some mechanical resonator is what I actually.
A strong one.
Okay. Well, it's actually a real pleasure for me to have the next speaker. This is Robert Blick. He's also a Rutgers student from I don't know how many years ago, but he's now he's now at University of Wisconsin. I think you're in Germany for
quite some time.
Yeah, quite some time. So again, this will be another talk. The title is Single Electron Tunneling in Nano-Electromechanical Systems. This is I'm sure also going to be low temperature kind of electron.
I admit it.
Yes. So I think this will be an excellent talk, and look forward to hearing it. And with that introduction, I'll let you go ahead and get started.
Thanks a lot. Thanks a lot for the invitation to give my talk here today. So that's going to be about single electron tunneling and phonons, and I think it nicely matches what we heard before. And I have to admit, by now I'm in engineering, so I always have to keep the numbers when it comes to millikelvin really small, right? So that the funding agents don't see it, but I'm going to admit it here whenever necessary. And basically, what shall I say? Yeah, this work, the outcome, what we're going to present today is sort of, single electron tunneling into suspended quantum dots. And I'm going to speak much louder now. You confused me. Yes, the work I started about 10 years ago, moving from Michael Lucas's group from Caltech to Munich for my assistant professorship, and I'll continue that at Wisconsin. And I hope to walk you through all the stuff we're doing right now in Wisconsin towards the end, and I really hope to match the timing there. Anyway, the deal is I'm focusing on what I indicated in the sketch, and that's going to reappear, building a little quantum dot in a aluminum gallium arsenide structure for now, and looking into what happens to the phonon modes. So in order to pitch this talk, a plot which I recently found that was actually published in The Economist some time ago is sort of interesting. It basically gives you the power density in typical Intel processors versus the years, right? And there are many things you can learn about this graph. First of all, you can learn about your own age, meaning that if you still remember those numbers, the 8086 or that stuff, then you're old. That's what I realized personally. And that was back in the days when 20 megabytes of hard disk was really good, and I was really enthusiastic. Anyway, but the message basically is something about the power consumption, power dissipation in these devices, in these Intel processes. And as you can see, we were still quite okay about 10 years ago when it came to the 486, but with the Pentium family, the power level, so the dissipation, considerably increased, right? And by now, and that's sort of the nice branching or reconnecting thing in the future, is that semiconductor industry finally comes back to nuclear fission and to high energy physics temperatures in the end when it comes to rocket nozzle temperatures up here, right? So in the end, that gave me sort of the excuse, I should say, writing these grants on considering not this extreme of high temperature operation and dissipating a lot of milliwatts here, but really looking into the fundamentals which were addressed in this nice talk earlier today when it came down to designing the phonon background and the electrons which sort of run through there and how dissipation actually works on the nanoscale. So that's sort of the outline of the talk. And apparently some time ago, I think last year, I found this other interesting graph from a publication by Rolf Landau in the 88 in Nature. I quoted it down here, and that basically gives you, so I apologize for the small writing on the left-hand side, but that basically gives you the energy in picojoules per transistor gate operation versus the years again, right? And what he did back then already in 88 is to simply look into the IBM files and go through all the processes and gate power consumption they had back then, making this plot, which is sort of an analogy to a more standard plot, but this now on the thermal basis, which ended up, and that's sort of the prediction that semiconductor industry runs out of steam, you can't say, but I'm looking for a better American expression, but runs into thermal problems maybe in about 2012, 2015, and that's what I like to say in my lectures. So this is when semiconductor industry will be just out of breath because you cannot store that a single electron, which might be your normal bit, so not the quantum bit for now, but you can't store it reliably in your single quantum dot transistor, whatever. And that sort of is the greater outline of the work I'm pursuing here. The focus And that's sort of the bottom line of what you want to probably remember is shown here in this micrograph. That's just an E-beam or a scanning electron beam micrograph picture of the standard devices we're working at. And that's an angled view, so what you see here are two structures. This would be a small suspended hall bar, right, where the thickness of this guy is about 120, 130 nanometers. And this is our quantum dot. Now, there's a specific feature which makes these devices different, and I'll remind you during the first part of the talk when it comes to processing. Specific feature now is that this is aluminum gallium arsenide, meaning it is equipped with a low-dimensional electron gas, and depending on how you design it, you'll have either a two-dimensional electron gas film in here, or if you add these notches, 1 and 2, you'll create these quantum dots, right? Where basically, if you bias it properly, you get a tunneling resistance, thus you localize charges of the order of 1 electron up to 500 to 1,000 electron, depending on the size of the structure you built here. Now, the crucial point, and this is what connects to nano-electromechanical devices, is that we suspended that, meaning that we undercut it, and that you can nicely see sort of in the shadow of the E-beam down here. So we removed the sacrificial layer, right? And now we end up with this phonon cavity, which is, again, crossing the boundaries of the field of NEMS and going a little bit more into quantum optics, if you wish, where we now design phonon cavities which can interact with single electrons hopping in and out, right? And that's sort of the baseline of the talk, and towards the end I'll probably lose it a little bit, showing you the recent results we got at Wisconsin. The phonon modes indicated, again, up here, right? Electron pops in, and then something happens with the phonon distribution in there. This is what the talk and the measurements are about. And finally, of course, you can also understand that in terms of different phonon modes indicated down here, where we're looking into flexural modes, but also torsional modes, whatever. So there's a full variety of different modes you want to be aware of. Now, the talk is structured as follows. So in the beginning, I'll just give you a feeling for the structuring of the devices, which probably is sort of interesting because in the talks before you have seen that it comes down a lot to the surface or edge roughness, right, when it is connected to electron-phonon interaction. Then I'm going to show you some sort of ballistic billiard measurements, which to us were sort of an indication of how good our suspended cavities are. And that is connecting to the old stuff of low-dimensional electron gas physics, where people did these Magnetotransport measurements. So it's a well-established field, which gives us the confidence that we exactly know what these single electrons in these cavities will do in the end, right? So good point here. And number 3 is something which Keith introduced before, which comes down to building displacement detectors and probably looking into the quantum limit, right? Next part, and this is where really the stuff, meaning what I pitched here with phonon blockade, comes into the game, where we all of a sudden see the interaction of single electrons hopping into the cavity, and I'll introduce you to that in some detail. And finally, down here, I'm going to lose it, right, and probably the chairman will drag me off away from the screen here. But that's sort of the most recent stuff we're studying when it comes to connecting maybe not phonons, but different topologies and low-dimensional electron systems. So I'm really going to then move away from the electron-phonon interaction. However, let's get started with the processing. So usually, when you all know this stuff, that's a standard wafer material, 2-inch wafer we get. The remarkable feature, though, is that, of course, they're expensive, and that's because these were grown by Werner Wegscheider in Germany and are equipped with this nice highest mobility 2-dimensional electron gas, right? And that's a difference to standard NEMS approaches, where the guys, of course, always have the sacrificial layer or in NEMS devices, so you undercut the device and get this mechanical degree of freedom. However, in our device, it was very tricky and very important to embed this low-dimensional electron gas, get the right layer sequence, and so on, right? As indicated over here, so I don't go into these details. But then to maximize the mobility in these devices so that we can indeed obtain a suspended electron gas. For the experts among you, usually you want to throw in a gallium arsenide cap, otherwise you're going to deplete the electron gas easily. So it takes some tricks in processing and, of course, in growth in the first place to realize these structures. And towards the end, actually, I will show you some of the recent results where we made those devices also in silicon germanium to be closer to applications, right? This is usually what you're faced in working in gallium arsenide. Someone says that, well, that's not industry compatible, and so on. Anyway, the structures and the processing we did then is shown here. Basically, it's straightforward. Difficulty is probably that you want to bring down a pattern on your semiconductor, right, which is, in this case, nickel, which is then the protecting layer for the dry edge. Dry edge then is crucial to get very nice sidewalls, as you'll see in a second. It turned out to be a little bit more tricky than I say here, and the students, of course, complain a lot because of this stuff. And this stuff should just indicate that we always had to use a double electron beam writing process. So we had to first deposit the gating structure, as you'll see later on, and then deposit this green stuff, which is just the etch layer on top of this material. And so first bring down the gold electrodes, and then the nickel etch mask, and the realignment, of course, had to be after it down to about 10 nanometers on that, so that was a bit tricky. However, next step was then this etching, and the picture I like very much is shown up here. So here are the two guys cleaning the machine, and that turned out to be necessary because for etching these structures, to get these very nice side walls, right, which is crucial in terms of electron-phonon interaction, you have to use for gallium arsenide chlorine. And if you open the chamber, you always have some debris around with chlorine, and that, of course, turns into HCl. And when they did not use the gas mask, and they got this, funky smell in their nose, and they got all upset and went to the hospital. But nothing happened, so it was all okay. But since then, it's very important to use your gas mask. Anyway, crucial point is if you etch it down, you want to have very nice steep sidewalls and minimize actually the physical damage, which is imparted by the chloride ions, which then leads to a depletion of the electron gas, right? The blue stuff would be electron gas, and usually if you etch it down, you have a side depletion, and that you want to minimize. If you don't do that, then you end up with structures which are just either have no electrons in them or just too big, which is away from the target too. So here comes the acidic chloride. Now we mill it down, and the final step for that is typical NEMS processing would be just to under-etch it. And that's sort of shown here, where we did etch it, put these samples in the hydrofluoric acid, and remove the sacrificial layer. And as you can see, these, apologize, not too big, but here we just fabricated some cantilevers. We tried to take a look at the mechanical stiffness of the devices and how they sort of bend down, and just prepared then the typical cantilevers which you usually do. Of course, in these devices up here, you cannot make the standard transport measurements or 4.2 points measurements, and that will be shown in the next graph. These were just for getting an impression of how good the etching process actually turns out to be. Anyway, so this will be our final structure, and as you can see then, what we need here is our quantum dot, which we can form in the center or in the vicinity of the material, and we have leads going out left and right. Now, here's a summary of the structures we built, and this is what I'm going to, dwell on during the next part of the talk here, which is the first structures you've seen already. Basically, either this quantum dot or studying transport, conventional magnetotransport in the suspended Hall bus over here. Of course, then you can combine that with a nanomechanical resonator, and this is sort of what Keith mentioned before. In his talk, though, he did not use these quantum dots fabricated in gallium arsenide, but he used superconducting junctions, so Josephson junctions, to then pick up the capacitive signal of this vibrating resonator towards the quantum dot. The structure above that is a coupled quantum dot, a two-dot device, and probably I'll put in some remarks in the end with these devices. Another device is shown up here again. That was really tricky in processing these devices with suspended gating layers which run on to the suspended two-dimensional electron gas. Here you have these two quantum dots, and the remark I just thought of before in terms of connecting to the first talk of this morning is, of course, that in these devices you'll end up with two discrete states, meaning you can nicely then study thermal transport in these structures, which would probably be a nice link to working with real molecules and just by comparing these results. However, let me continue by going to the ballistic billiards, and basically that comes down to the following measurement. So if you don't know magnetotransport in two-dimensional electron gases, you probably don't like the slide. If you're well experienced with it, you're like, okay, I love that. But basically what we did is in these maybe a little bit detailed slides is to study the difference between the non-suspended cavity, if you wish, and the suspended cavity, right? So again, magnetotransport, just a standard way to characterize low-dimensional electron gases. And in this measurement, we simply did not undercut the device, so we sort of can look at our structures and what actually happens when the bulk of the material is still connected, right? So this is what it all comes down to. We completely, or did not completely, yet modify the phonon density of states as we did on the other end. Now in this graph, there are several things you can actually learn. So of course you see plotted resistance versus magnetic field. Large magnetic fields at low temperatures, so I admit it, just for characterizing the samples. And at high magnetic fields, what you see is that the structure is nicely symmetric, right? So that's good. So we didn't screw up in the fabrication. Now the striking difference, though, if you look into the suspended device, is that the overall resistance around the zero field region, which is the important region, rises, right? And there's a lot of fine structure going on, which you do not see in these sort of non-suspended devices. At higher magnetic fields, as you know, they're just Shubnikov-de-Haas oscillations, so just dominate the transport. And that is, of course, also seen in suspended structure. And that basically comes down to the fact, and that's sort of the punchline here at this part of the talk, that what we have to consider now is the ballistic transport of our electrons through these cavities and Hall bars up here in this very small graph, right? Meaning that as long as our electrons move ballistically, they can be sort of scattered from the phonons. But if you increase the magnetic field to large values above 5 Tesla, the cyclone orbit is very, very small, and then you don't see sort of the ballistic electron-phonon interaction any longer, but you only find this Shubnikov-de-Haas oscillations. So again, very straightforward. Meaning, sort of shortcut now, interesting point is down here in the low field region, and this is what we zoomed in here. And Eva White, the student who did all these studies in detail, really spent a lot of time analyzing that. And again, we just compare non-suspended, suspended, and then we zoom in into the field region around plus minus 1 Tesla, right? And now the interesting point is that apart from the DC resistance, in the suspended region being much larger, well, not much larger, a couple kilo ohms, what you find is this fine structure here, right? First of all, center peak, which is related to weak localization, so you can really go into the details of electron transport in two-dimensional electron systems. And you see another periodic structure, which is again symmetric in magnetic field, right? And that Eva found in her detailed studies, just comparing that to the literature, is related to different scattering mechanisms, and that should just underline the strength of our approach here. Meaning that we had all these different samples, and basically you can categorize that in the blue and the green stuff. I apologize, in the back you can't see the green head here. So the green head here is a coherent backscattering mechanism, which was actually found earlier by John Bird, right? While the blue stuff is a periodic oscillation, and that corresponds to the coherent forward scattering. So in both cases, what we see is sort of the edge roughness of our electron, let's say, phonon interaction, which is then reflected in these resonances up here. And that underlines the strength of the method now that we have this very good control of our low-dimensional electron gas in this system here, and can now tailor nicely, of course, the sort of the outskirts or the phonon environment. And that'll be the point here also made in sort of connecting that to the real world and maybe to the program manager, who should look into that in terms of funding it, meaning that what you can do with the electron beam definition of the structure, and of course with the heterostructural growth, is to nicely tune the density of states of your phonons, as we heard in the first talk today, and combine that now in the end with your low-dimensional electron system. In this case, we left these gates open. This is why they behaved as a cavity, while later on we'll sort of squeeze these tunneling barriers and confine the electrons in the quantum dot, right? So by using, just to repeat myself once more, electron beam lithography and all this stuff, we do not only have control of the electron system, starting from 2D, 1D, and 0D, but also we can now control the phonon densities of states with this approach of molecular beam apopexy and electron beam writing.
Are these coherent oscillation how related to Aronoff-Bohm effect?
No, they're not related to the Aronoff-Bohm effect, but I think, let me see, I think
it's very inside this loop, isn't it?
Yeah, but the periodicity didn't match, and I had some discussion here with Charlie Marcus about that, and I think the periodicity, if you calculate the H over E, it doesn't really match the size of the structure. That's what I thought before, because to us, it was crucial to actually see how big the electronic system is, right? And that's where I thought it would be home oscillations. I think there is a relation, and Barzal Schuler gave me some wise remarks which I forgot. I apologize for that. But I think there is a relation, but you can't say that it is home oscillations because simply due to the fact that you do not, I think that was it, that you do not have an opening. It's not donut shaped, so you cannot exclude scattering sort of through the center, right?
Yeah.
And I think this is what this paper is about. And for the details, actually, for when it comes to coherent sort of backscattering and coherent forward scattering, I would refer to those papers. And those guys, about 10 years ago, spent a lot of time analyzing that. And I mean, we only used it here to sort of calibrate our samples, right? And that gave us the confidence that all the other stuff in the end really works out.
I have two questions. The sample-to-sample variation you're saying is due to the edge roughness, which you cannot really control, right? So a priori, you don't know which one you're going to get.
This is in detail. I think it's true, but so do you want an answer from a physicist or an engineer?
Give me both.
Okay. The physicist would say it's very interesting because what the different periodicities, you know, the small stuff here reflect is a different surface roughness. So this is worth studying. While the engineer would say it's the fault of the RIE, the dry etching process, and the machine we used is a very nice Oxford plasma system. But you know, if one user uses it, another one uses a different flow rate, and blah blah blah, that then results in the fact that we have slightly different etching parameters, right? And then if you really engineer it, I think you'll come down to much more reproducible results over here.
Okay, and the other question is, take the same sample, you do another cool down. So this is a physicist question. You get the same.
There I would have to ask the student, I think, but they're very similar. I made the studies with the first devices at Caltech, and they're very similar. I think what changed was the amplitude of those, but you could reproduce the features. But I can look up the Fourier transform. I mean, I deleted this slide from the talk here, but I can give you this data later. Actually, I should have it here. Anyway,
I have one question.
Oh yeah, sure. Hey.
So one of the other differences between the release structure and the supported structure is the fact you can get strain relief in the release structure. So is there any effect of a strain component in the layer that is apparent in?
Good question. What we saw sometimes in using nominally unstrained aluminum gallium arsenide is that they buckle a little bit. And I think this shows up right here where the resistance goes up from 15 to 20 kilo ohms. So that you have some scattering mechanism which is due to the change of the band structure, probably. Okay. I believe. But I'll address that later on. We're actually in the final measurements, and let me just skip to this part then, where we embedded then a strain to actually look into quantum transport in curled up structures. So, but just let me come to that towards the end here.
There's no period in 1/B?
These are not period in 1/B, these are period in B, and this is why you'd like to relate that to Aharonov-Bohm oscillations. But I think, coming back to the literature, you're not supposed to call them Aharonov-Bohm oscillations directly. This is what people call them coherent scattering oscillations. The 1/B dependence is the Shubnikov-de Haas effect at larger magnetic fields. This is when the orbit here is much smaller than the size of the electronic system, and so that you end up with a typical quantization in terms of Landau levels or edge channels, right?
Also, there's a 1/B oscillation at below 1 Tesla. It's discovered recently by Louis Duskour at Utah and San Diego due to phonon emission. Not just Shubnikov.
Well, I don't think that we'll see that here because of the etching. The mobility was a bit reduced, and I think Dan Zui likes to have very high mobility structures.
Yeah, that's a high mobility.
High mobility, and we started out with 250, so a quarter million, but that was reduced by a factor of 10 in the early structures, so that the two-dimensional electron gas was worse than before, right? And this is where the etching sort of destroys maybe nice coherent features, but we still were able to see the scattering effects. All right. Let's now put in a fast reminder of what Keith was talking about, which is now using quantum dots as detectors for NEMS, right? And this is just an application which is very important for any kind of scanning probe application, or if you like to look into what he does, very low temperatures and quantum states. And what we did, and this graph is sort of just a reminder, is to then bias this structure to achieve a quantum dot down here. And this is probably what you want to remember, because we studied transport before in these Hall bars, and right now we just use it as a gate to see what actually happens if we pinch off these barriers or form nice tunneling barriers and then send through single electrons, right? So we want to establish now the regime of single electron tunneling and see what happens with electrons bouncing around in the single phonons, just a circuit diagram. And this is what we got. And if you don't know it, just give me 1 second to give you a very brief introduction. So usually we focus up here on conductance versus gate voltage, and we see these nice single electron peaks, right, and good Coulomb blockade. And from this measurement, of course, we can directly determine the number of electrons we have, the energetic, the drain source voltage, and of course the Coulomb blockade energy. And then you can switch over, as Keith has done before, to these grayscale plots, and you see these excited states, the ground state in this line, so just tilt that, right? And what we found in this particular device is that we had, and that's sort of the important number on this slide, about 500 electrons in these cavities, or in this cavity. And first part now would be, of course, to look into the limits, quantum limits of displacement detection, as Keith did. This is why I want to put that or keep that very short. Difference in our device now is that we added this NEMS resonator, just a single gold beam which now wiggles around, and of course now can study transport through our quantum dot over here, get the quantum dot conductance resonance focused onto the operating point, right, and get the same numbers, although not as impressive as Keith, numbers of about charge sensitivity and displacement sensitivity of about 10 to the minus 4 and 10 to the minus 3. Meaning these devices are very interesting for SPM applications and the stuff which Keith has shown. And this was just an older summary which I put in here. I just wanted to point out that other people in the field, so this is I think by Keith Group, and this is by the Cleveland Group in Santa Barbara, who also work on this topic. But as promised, sort of with the first slide when it comes to power dissipation, I want to leave this topic right now and not focus, and that's sort of the bottom line, and don't go into all the details here, but not focus onto the capacitive interaction of a NEMS resonator with a quantum dot, but stay in the quantum dot and see what actually happens when I send single electrons through the quantum dots, right? So this would be coupling that to the environment, and Keith, I think, gave you a very nice introduction to that, to his latest results. I'm going to switch gears and come to the sort of main part of my talk, which is taking this single suspended quantum dot and now looking into what happens with the phonons. All right. Meaning, and if you want to have sort of an overview, what we did here is to bring that together in terms of a zero-dimensional electron island with discrete electronic states, and coupling that to our phonon cavity with a big point now that in the end, if you do so, you create these Fraunhofer singularities, which are normally, of course, in the phonon density of states, right? And of course, if you bring that together, then you have your electron phonon cavity, which is very nice in comparison to quantum optics, right? Where people worked, of course, for more than 10 years to design these high finesse cavities, sending through a single atom, then trying to figure out sort of the details of the QED measurements, how the single atom in the cavity would interact with a released phonon mode. And basically, this is right now sort of termed quantum electromechanics, and applications, what we focus on right now is more dissipation. All right, so before actually, and this is where put in a little microsecond, before I didn't show you the whole truth, because in these measurements what we found is actually at zero bias, without any magnetic field applied, we didn't see anything, right? And that was sort of the horizon of funding these days, I guess, so it's very empty. But all of a sudden, when you then increase the drain source bias, right, apply certain energy to the system, what we found then is that we still see affinity conductance through the system. And the question now is, where does this sort of gap come from? where does this effect in the center come from, that we do not see any conductance, because that is what should be there in the first place, as we found that in many unsuspended quantum dots, meaning we had to figure out how this suppression of conductance comes about. And this is just zooming in, showing you another strength of the method, meaning that we now can directly determine the energetic width of this sort of missing resonance, which is of the order of 100 microelectron volts. And this is exactly what we then had to relate to what is going on with the phonon modes inside the system, right? So this is what this whole talk is coming down to, mainly then analyzing these structures, measuring it out, and then varying the typical parameters, which are temperature, bias, you've seen already, and of course magnetic field, etc. So the explanation we found for that, also in comparison with theory, is the following. What we did is to ask these guys in Germany to do some simulations, and basically we looked at our structure here and tried to come up with the right phonon modes, which then will interact with our single electrons hopping through here, right? And what they found is, and that's sort of a nice graph to remember, is they looked into all different phonon modes there are. In gallium arsenide, what you have is, of course, piezoelectric modes, but also displacement modes. And of course, due to the structure of this bridge here, right? So it's not a simple buckyball. You have many flexural modes and torsional modes, meaning you end up with a lot of sort of density of states plots versus energy, which now strikingly, and that's sort of the important point, I think, if you don't want to remember the rest, this is what you want to remember, is that the dashed line in the back just gives you the standard curve of a 3D bulk system. And in their simulation, what they found is these spiky lines for dilatational modes, and for flexural modes, the other spiky line is a certain offset, right? Which comes down to exactly what I said at the beginning, that due to the limited dimensions for the phonons, we do see discrete states in the phonon density of states. And what we now have to analyze is what kind of acoustical phonon mode is actually possible in our cavity, right? For that purpose, what we do is to look up the velocity of sound gallium arsenide in a specific direction, which is usually of the order of 4 kilometers a second, and simply scan through the thickness or width. And if you do so, what we found here is that for one particular mode, which gives us an energy of around 150 microelectron volts, corresponding to a 35 gigahertz phonon, we get exactly the right energy match, right? Which means the electrons which hop into this cavity must release a phonon and thus block transport for the next consecutive electron. And apologize for this being a little bit tricky, but this is actually what this talk is about, that we can now play around with this density of states for the phonon, design it properly, and for the engineering aspect, the important note would be here that if you do that properly, right, you can sort of vary your electron energy along these lines and probably even achieve or build a dissipationless transistor, because the electrons at this particular very small spot here, right, they would simply not find any phonon to dissipate heat. So this is sort of for the engineering aspects where we now look into designing the right phonon density of states to reduce or really rendering dissipation obsolete. Now, more details on that, and this is what we did when we looked into sort of classical literature of molecular quantum mechanics, and I have the rundown down here, and this is probably the best way to analyze that. So this is the standard picture for a non-suspended quantum dot, or for a molecule if you want that, right? So you have Fermi levels left and right, and the discrete state. And the discrete state we can now change nicely by applying a gate voltage or playing around with a drain source bias. However, important question was that this resonance all of a sudden disappeared in our measurements and only reappeared once we changed the bias, the window, or once we increased the temperature. Now what happened is the following, that the electron, the first electron, runs into the cavity and emits a phonon, right, where this energy was exactly determined by the bias dependence, which is of the order of 100 microelectron volts. Okay? And that means, of course, that now the energy level is shifted down here and no further electron transport is possible. Now, if you look back into the literature of this stuff here, of quantum, the original molecular quantum mechanics, you'll find that this effect is actually called the Franck-Condon effect, and we just pitched it phonon blockade because the transport was blocked by a phonon which is released into the cavity. And what that stuff basically means is, and these are the level diagrams from the original publication, basically is that you have an intermediate step, right? So you have this excited state, and then you have a phonon release, and then only the electron can relax to its ground state. And this is exactly what we have going on in our cavities, meaning we have this internal degree of freedom, which corresponds to the very, spiky density of states. So, and a phonon gets sucked out of this electron's energy, and thus we find this misalignment at other energies. Of course, you can double check that, and this is what we did in further measurements by changing the temperature, and this is just repeating the plot. Maybe just first look into the stuff up here. So at lowest temperatures around 100 millikelvin, we don't see any transport. Increase the temperature slightly to around 400 millikelvin, transport reoccurs. Yes.
Is the electron phonon coupling stronger in the dot? How come it does not emit phonons before tunneling?
I think that's a very good question. And let's see. So usually the electron phonon coupling, this is what everyone assumed, right? Like in the 90s, original papers, electron phonon coupling at low temperatures is weak, especially if you go to very small dots. Okay, so phonons should not be considered. However, this was only looking into quantum dots which were sort of attached to a substrate. In this case, we remove the substrate and get this nice Van Hoven singularity, right? Which means that the cavity really likes to have a phonon once an electron with too much energy enters the quantum dot. This is one point. Second point is it doesn't occur in the leads because the electrons are not localized, right? In this measurement, we put in the tunneling barriers, which means that the electrons have a certain dwell time in the dot before they can make it out. This dwell time is enough for the phonon to be emitted, and then the energy level is lower, and so the next electron cannot tunnel through.
So the resonance energy is matched to the maximum energy phonon density state. That's how. Yes,
and this is what we found in the comparison to the theory guys who did the detailed calculations. And from that we found it's sort of this thickness phonon component you have to consider, which matches nicely with the resonances we found over the energetic gap we found here, and it also matches with the temperatures. So that if you compute that, compare that to the KBT, right, you get the same energy out of that.
Apparently, good phonon dissipation. The phonon thermalize fast.
The phonons in the cavity do not thermalize fast.
And it gets very hot.
Yes. So in a way, I mean, I agree. We sort of showed the opposite, but we showed that in this particular measurement, that the electron-phonon interaction is really enhanced in these nanostructures. And I agree, this is what you want to avoid, right? So you want to have a mismatch, and we just happen to have the electron energy exactly at the Van Hoven singularity, at the energy of the phonon, so that the phonon is dispersed into this cavity and bouncing back and forth. And actually looking through the literature, and this might interest you, this is from a paper from Yoon's group, now also at Cornell. What they showed is, you might know that or not, is making transport measurements through a single buckyball, right? And they were looking at the electron-phonon interaction at a larger drain source voltage, meaning they looked at these lines here, which are the excited states, which they say correspond to either this mode or maybe flexural modes like that, right? And this is what we were after before as well. But what we found is this phonon blockade gap, and actually they found that as well, because if you zoom into the structure, you see this gap right here, but they didn't address it. So I asked them about it, and I think they might look into that. But this is what we assume is the similar effect, which is in classical quantum mechanics just called the Frank-Condon principle. So it's well known from that end of the spectrum, but it also sort of reiterates the fact which we had heard this morning, that either you take a real, well, sort of a semi-real atom, or real atom, or our artificial atoms, which are the quantum dots, and you get sort of the same features, meaning all the stuff which was addressed about the phonon, designing the phonon density of states, you can actually do now with these devices. And then we stop this stuff here and go back to the sort of the outlook in the end, where we now try to get even better and address some of your questions, which is now using these devices, again suspended devices, but now with gates on top, right? So before, the weakness you could criticized that was that we worked with a bar which has these notches, meaning the tunneling barriers were sort of fixed, right? And in these devices, and that's what I'm going to show you now in a second, is that we can sort of apply bias here and tune into a single, or hopefully in the end into a double quantum dot device. And then we can nicely also prepare the dots or the electrons with a specific dwell time in here and test out then the interaction with the phonons in more detail. And first measurements we did was simply on a suspended layer with and without gates, just to test the effect of the gates, right? And here it's getting tricky again, sort of, if you really look into the details, because simply putting gates, metallic gates, on top of this piezoelectric gallium arsenide slab changed then sort of the scattering mechanism which you asked about before, and that's seen again nicely in these now magnetoconductance measurements. So I switched here from using the resistance to conductance, which is okay at high magnetic field. And what you can see basically is the gated stuff is much lower than the ungated stuff, and that means that we do not only see roughness scattering of electron phonons at the sides, but also because we're simply putting gates on top. However, the good point here is that we still see conductance through the system, even with gates on top, and now we can go ahead and try to tune in single dots or quantum point contacts. And this is shown in the next slide, and I'll probably refer them to the publication for the details here. Meaning, what we did sort of nicely, or a little bit shown up here, is to now first bias a single gating barrier, right? And what you get, and I think Keith mentioned that briefly with the thermal quantum conductance, is shown here, which is now, of course, the electrical quantum conductance, which is proving the point that we get sort of a good quantization in this channel. And that, again, reiterates the fact that we can design our phonon system, but with the help of the gates. Now, we tune in from a 2D system, which you've just seen on the previous slide, to a 1D system, and apply a magnetic field, if you wish, so we get a better plateau, which is the quantized level of 2E squared over h, or even go to the zero-dimensional system by now tuning in 2 of those gates, right? And that's sort of shown here. These were the first results we got. Actually, at 4 Kelvin, this is why the sort of these resonances, which are first indication of Coulomb-located resonances, are not too well pronounced. But that means now we can nicely cover the whole range of low-dimensional, electron gas physics, and now we only have to change sort of the topology of the suspended semiconductor membrane. And instead of looking into this 2-dot device, what I decided now is to probably, which is summarized over here again, what I decided now is to bring up some new stuff, which is looking into strain engineering of these structures, right, as you asked in the beginning. And these will be sort of the last slides, so that I can stay in time somehow. Meaning, what we did now is, and that's work done with Max Galli's group at Wisconsin, is to actually switch to silicon, right? I mean, he's a silicon expert, and that's much better for application as well. However, what he can do is to, of course, then use the standard SOI material with a sacrificial layer. It's this buried oxide, so nothing fancy. But what he can do is to grow a silicon germanium layer on top, right? So we get the same functionality as with the gallium arsenide, where we can again embed now a tritium electron gas. So simple. Point now is that what he specializes in as well is to add a strain to these layers. Meaning, if we do the standard processing, right, we structure the semiconductor membrane on top somehow, it can be anything you want, have our oxide beneath, dip etch it into HF again, we release it, as shown here, but what happens then is that your strain changes, right? So if you design it properly, if the strain on both sides is designed in such a way that it's just released properly, then the membrane stays flat. What I'm after in the end, of course, is that what we wanted to have is an uneven strain, so that the membrane actually curved up, so that you all of a sudden have a topology which is defined by the strain embedded in the material with a low-dimensional electron gas, which is indicated by this red layer here, right? So that's sort of the bottom line. Processing now works as follows. That, of course, you can later on attach it to any substrate. And again, that's sort of the engineering background, because a lot of the thin film, fast electronics is about putting then these membranes, but very large pieces of these membranes on any kind of host substrates, on plastics, and other guys in our department, Jack Ma, is working on that. What I focus on, as I promised, is to look into what actually happens if you have a strain embedded and release now the oxide layer, right? And this is a little sketch which Victor Prince gave us. So as you can see, oxide is removed, the stuff curls up, and in reality, that's a sort of a little movie clip I brought here. And these are tiles we're fabricating now. And what you see is, this is a tile of about 30 microns square. The HF is attacking that, and as you can see, all these little tiles sort of curve up, right? And they form these little tubulars, and of course you can do so over many, over a whole wafer, and what you get out of that are structures like these, so nice noodle-like structures. Again, you can switch to different geometry simply by changing the lithography, E-beam or optical lithography. But all of a sudden now, and that's sort of the new aspect, that we now incorporate topology into electron transport, right? And right now these structures are only nice to look at, but what you'll see in the next step will be the first measurements where we attach contacts to this device and actually study then electron transport at these levels before. This is just an outline, and since the chairman got up already, I'll skip over that. And just briefly, so this, you can also build these nice semi-membranes, and they're folding and whatever. So you have this mechanical degree of freedom again, and that allows you now to build this thin film flexible electronics, right? That's the stuff down here. If you want further information, just ask me and I can connect you with the right person. But that has a lot of implications for, let's see, optical devices like phonon bandgap materials, or just forming new heterostructures, and I'm happy to give you more information after the talk. The point I wanted to make, and that's sort of the last stuff here, that we can now release these membranes, and that's done quickly, where this purple stuff is released, then a Hall bar is formed, and we can measure transport. And since I promised the topology, but running out of time, the next step would be then to not use a strained balanced material, but an unbalanced material, and to actually look into this effect where we under etch it, and the tube firms, right? The background, and that's sort of my, my love to physics, is shown here. Earlier paper of ours. If you do so, and that's the nice physics about it, what should happen is that a geometric potential should form, which is related to Barry's phase actually, and this is what we're after. However, the radius of curvature for that is very small, 100 nanometer. What we have right now, in the last slides is shown here, the size of this tube is of the order of 20 micron, and this is just a Hall bar around it, so we contact it, make the transport measurements through this curved tube, and what we get are sort of, if you're an expert, not very good Shubnikov-de Haas oscillation, but what we see is, if you illuminate it and apply backgate voltage here, is that we see the first indications of Shubnikov-de Haas oscillations, which means now, and that's sort of my last message here, which means now, what you have now is a two-dimensional electron gas to which you can add topology, right, by curving it up, looking into the original sort of analysis of the fractional quantum Hall effect. And with that remark, probably I want to end and want to thank for theory support shown here by this nice FemLab simulation, and I want to thank all the guys involved in the project, and especially Eva, who did a lot of the work on the suspended aluminum gallium arsenite, and my group at Wisconsin right now, and the collaborators over here. And of course, funding is from NSF through the MERSEC. I want to thank you for your attention.
Well, thank you, Robert, and I'm going to cut questions short so that we can stay on lunch schedule. But I really appreciate